Okay, so last two sections for this week, 8.3 and 8.4, are kind of like their own unit, just like 8.1 and 8.2 were. We're getting away from like solving triangles and that stuff. We're going to look at complex numbers and how we can write them a different way. Okay, so I'm going to go through a few things real quick, just review. A plus bi, that's called the rectangular form of a complex number. Real part could be plus, could be minus. Then you have an imaginary part, which is the b, and you put an I next to it so the person knows looking at it that what's in front of it is the imaginary. A plus bi. For adding and subtracting, that's the best way to write a complex number. It's very, very simple to add and subtract. But multiply, divide, powers, and roots, that notation is not the best way to write complex numbers if you want to start to do things quicker. So to get into the other way to write complex numbers, first we just have to talk about how we would graph this. I thought we had already talked about it. Maybe we didn't. So I'll talk about what I showed you right now. So if you want to graph a plus bi, you can do it on what's called the complex plane. And basically, if you can graph a comma b, that's exactly how you graph a plus bi. In the complex plane, your real axis takes the place of the x value. That's your real. The imaginary axis is taking the place of your y. That's your imaginary. So the real is like your x. The imaginary is like your y. And in a minute, you'll see why we graph complex numbers, because it's going to tie in with the next step. Okay, so any question on the complex plane? You cannot switch those axes, just like you can't switch x and y. X has to be horizontal, y has to be vertical. Real is horizontal, imaginary is vertical. Okay, let's just try a few examples. All right. So starting from the origin, how would I graph -4 minus 2i? How about Derek?
It's going to end up in quadrant 3, so you go 4 to the left.
4 to the left. Yep.
Down 2.
And then down 2. So that's -4 minus 2i. Yep, that's it. Scott, how about -2 plus 3i?
Go to the left.
Yep. That's -2 plus 3i. Peregrine, how about 5i?
You just go up 5.
Yep. So that's kind of a special one because it's on an axis. It's not in a quadrant. We'll talk about what that means. And Sam, how about 6? Yeah, you can always think of it as 6 plus 0i. So it's like 6 comma 0. Usually if it's a 0, we don't write it. Same thing here. You could think of it as 0 plus 5i. Any questions on that? So that's graphing complex numbers in the complex plane. Very, very, very simple. All right. I want to look at how you would find the absolute value of something like that. What does absolute value mean? Like, means the distance from 0. Now, when you're talking about a complex number and you're graphing it, we don't really have 0 because it's 2D. What do we have in 2D that takes the place of 0? Origin. We call it the origin. So if you wanted to find the absolute value of, say, -2 plus 3i, what you're looking for is that. That's the distance from 0, except it's two-dimensional. It's the distance from the origin. And how do you think you would figure out the length of that black line segment? Yeah.
Pythagorean Theorem.
Yeah, we just use the Pythagorean Theorem. 3, 2, and that would be the square root of 9 plus 4. and that would be your absolute value. So it's really just using the Pythagorean theorem.
What would you do on x? Is it just like the number of faces, even on like the I'm talking like the imaginary x, like the real x, not be like x, but like
You'd still count. You could just count.
five.
Yeah.
Alright.
I mean, you technically can still use Pythagorean theorem. It would be like 5 squared plus 0 squared equals hypotenuse squared. But when you do 5 squared plus 0 squared and then take the square root of it, it's just the square root of 5 squared, which would just be 5. So the absolute value of the complex number a plus bi is real part squared, imaginary part, which is just the b squared, add them up and take the square root. So it's just the Pythagorean theorem. Right, so we haven't started writing complex numbers in a different way yet. We're still writing them the old way, a plus bi. But graphing is going to connect with the new way. And so will this. So we're kind of building towards it. So let's find the absolute value of 3 plus 4i. So to go back to the formula, real part squared plus imaginary part squared, take the square root. Okay, what's the real part here? 3. So square it. So that's one side of your triangle. What's the imaginary part?
Or
Just the 4. Some people say 4i. It's not 4i. It's just 4. So square each one, add them up, and then square root. And that's going to give me how much? 5. So absolute value of a complex number is the same idea as absolute value of any other number. It's the distance from 0. In this case, the origin. So a little more complicated to find it because it's 2D instead of just on a number line. Questions on that? Okay. So, all right, let's take a quick look at this. So I'm going to show you just more of a concept than an algorithm for doing something of how you can add complex numbers visually. Okay? Like if you actually had them drawn out. Okay? So this part, it's going to be kind of hard to put in your notes because I'm going to drag some things around, but it's more of a conceptual thing than a process. All right, so suppose we had 2 complex numbers. That one has a real part of A. That one has a real part of C. That has a real part of B. And that one has a real part of D. So remember, the idea when you're adding complex numbers is it's like you're combining like terms. So I just made up 2 imaginary locations for A plus BI and C plus DI. What I want to do now is just try to visualize the real and the imaginary part of each coordinate, but not as a number, as a picture. Right. That's A. That's the real part. This is B. That's the imaginary. Any question on that? I'm going to do the same thing for C and D. That's the vertical. That's the imaginary. You're not going to see this one too well, but you will in a second. That's the real. So, how many different parts do I have here? 4. I have an imaginary and an imaginary. I have a real and I have a real. And if you want to visualize what the answer would be on the plane, you could go like this. Take the real plus the other real, and then take the imaginary plus the other imaginary. It's not perfectly straight, but that point right there represents adding those 2 together. Okay? So it's like you just combined like terms. Any question on that idea? So this is the point A plus C, comma, B plus D. And that's exactly how you add complex numbers when you do it with arithmetic. That's how you could do it visually. Think of it as pieces you're stacking together. So that's what I meant by geometric. I just wrote that down. So the complex number z1 plus z2 is represented by that coordinate. A plus c, comma, b plus d. Not a super important idea, but just just a different way to think about adding complex numbers as a visual than just arithmetic. Let's see that. Okay. So what we're going to spend the rest of today and tomorrow on is first figuring out how to write a complex number in a different way called trigonometric form. And then once we do that, we're going to learn 4 things that allows us to do very, very nicely. Multiplying, dividing, raising to powers, and taking roots. So, when we write a number in trig, the regular way, right? It's basically written like this. You have a real part, which is represented on the x-axis. That's why I used x this time. And you have an imaginary part, which is represented on the y-axis. That's why I use y. You could use a and b if you want. It doesn't matter. It also doesn't really matter if you put the I before the y or after. I know when we write an imaginary, we normally do 2i. We don't do I2. I put the I before it because that's how your book is going to do something in a second. So, horizontal, vertical component. That's rectangular form. In trig form, we don't care about the horizontal and the vertical. What we care about is basically something like this. This. Except I didn't want to mess up my triangle I have. Okay. So when you want to represent a number in trig form, the idea is from the positive x-axis, you could rotate a certain amount of degrees to get there. That's an angle. And then you have a distance from the origin. That's what we just practiced that. That's basically the absolute value. So those are the 2 things that you need in order to write a complex number in trig form. We eventually have to figure out a radius, which is like an absolute value, and an angle. So what you would be given is x and y. So what we're going to do is we're going to take, I wrote it right here. That's the format we've been using. We can't have x anymore. We've got to get rid of x. And we can't have y anymore. We have to get rid of y. In trig form, you're only allowed to have a radius and an angle. That's trig form. So, let's start with dealing with the x. From the perspective of this angle, what would the name of this side be? That's adjacent. And this side? Hypotenuse. And what trig function involves adjacent and hypotenuse? Cosine. One of the 2. So, cosine is adjacent over hypotenuse. Now, I want to get a formula that I can substitute in for x, so I need x by itself. So what would x equal? r cosine theta. In a second, I'm not going to do it right now, but I'm going to plug that in for x. So that's a formula that allows me to get rid of the x and convert it to r's and thetas. That's trig form, r's and thetas. Right, now let's do sine. What's the name, the only side we haven't labeled yet, the y? Opposite. And sine is what over what? Opposite over hypotenuse. So that trig function is perfect to use because it involves the y, which we want to get rid of, and the r, which would be something that you use in trig form. So when you get y by itself, what's y? R sine theta. So now, take that and fill it in right there. If you make those two substitutions for x and y, you're going to have what's called trig form. Pretty much. There's one thing we have to do, but it's pretty much trig form. All right. So start with x. What am I replacing x with? All right. So let me do that first. R cosine theta plus the plus and the I stay right where they are. And what are we replacing the y with? R sine theta. So now, look at that. Interesting. That's never happened. So now we have that. But what do both of those terms have in common in front of the trig function? R, so we can factor it out. And that is what you call the trig form of a complex number. It's R, in parentheses, cosine theta, plus I sine theta. So there's two things that you have to find to write a number in trig form. R is the radius of a circle, and that's basically like using absolute value. It's the hypotenuse of the triangle. And theta is an angle. So we're gonna practice finding that angle. Yep.
Okay, so this is kind of weird. But like on a unit circle, like radius is always one, or really with any circle where like the radius like on the axis is like the same. Like wherever you go on the triangle, right, it will just be one, right? Because it's still a radius. Do you know what I mean? Like it's just be the same.
The radius? Well, it depends on the coordinate I give you.
How? Because it doesn't matter where you start, right? Because the origin, the difference between the origin and the outer circle, if it's a straight line, it's just going to be the same, right?
I mean, if I give you the coordinate 2, 2 versus the coordinate 10, 10, 10, 10 is on a much bigger circle than 2, 2.
Right, but like it'll still be the same as like it's the same, right? Did you know what I mean?
I mean, there are other coordinates that would be on the same circle, but we don't have to worry about other coordinates, just this one. So, when you write an answer in trig form, a final answer would look like this. I'm just making these numbers up. That's a final answer. You don't do anything else with that. Okay? If you said, well, should I take the cosine of 15 and then distribute the 5 to it, and take the sine of 15 and distribute the 5 to it, then you would be changing it back to this. So if you do that all out, you're going back again. So we don't want to do that out. Okay? That's considered a final answer in trig form. You solve for this, and you solve for that, which is the same as that. The angle is used twice. So, theta is the angle with the positive x-axis. So if you had a coordinate over here, there's your radius. There's your angle. If you had a coordinate down here, there's your radius. There's your angle. So any questions on what the r and the theta stand for? Okay, so how do we get r and theta? Let's start with r. That's r. So I'll give you a point in standard form, which will have an x and a y. You want to think of that point as being on a circle. So what shape could I make here that would help me find r?
Triangle.
Just make a triangle. You already have the third side right there. And how long is the bottom side?
X.
And the height?
Y.
Y. And that's r. So, how we basically just did this. How would you find r? Yeah, Pythagorean Theorem. And I think on the next page, I write this down nicely. So, I'm not going to write it here, but I just want you to get the idea. Use Pythagorean Theorem. Now, how would you get theta if you knew x and you knew y? What trig function would you use?
Tangent.
Tangent. Tangent of theta equals opposite over adjacent. Now that's not theta though, that's tan theta. Take the inverse tangent. So we're going to write that down on the next page, but that's where the ideas on the next page come from. Inverse tangent and Pythagorean theorem. So, to find r, use the Pythagorean theorem. To find theta. Now this is finally going to tie in with what Pat had asked me, why would we have to graph it? Because the problem with inverse tangent is inverse tangent will always give you an answer between negative 90 and 90. That's the range of it. That's the answer that you always get back. If you put in a number on the calculator, press inverse tangent, and hit enter. What comes up on the screen is between negative 90 and 90. Negative 90 to 90 would cover which two quadrants in that picture? Would only cover 1 and 4. Well, you could definitely get an answer in quadrant 2 if you had a coordinate that was a negative x and a positive y. So, depending on the quadrant you're in, we're going to have to make an adjustment to just using inverse tangent. If you're in quadrants 1 and 4, it's fine. Okay? You just do the inverse tangent of your imaginary over your real, y over x. But if your point is in quadrants 2 or 3, and how would you know it's in 2 or 3? The x part of your coordinate would be negative. The y could be anything, but the x would have to be negative. This part of the circle is on the other half from that part of the circle. So what could you add to something to move to the other half of a circle? You could add 180 or pi. So if your answer is in quadrants 2 or 3, you're going to take inverse tangent and you're going to add pi or 180. Now this covers how to find r no matter what quadrant. Pythagorean theorem works in any quadrant. This doesn't cover everywhere your angle could be. It covers if your angle is in quadrants 1, 2, 3, or 4. Where else could your angle be? On the axis. Well, the problem, if you try to use one of these formulas on an axis, what's the coordinate of that point?
0, 7.
0 something. The key is it's 0 for x. If you try to plug that in right there, what would happen? It's undefined. You can't divide by 0, which is why if you're on an axis, you basically just have to memorize it's one of these 4. If you went right, it's 0. If you went up, it's 90. If you went left, it's 180. If you went down, it's 270. So how can you quickly tell if you get a coordinate and it's on an axis? How would you know right away just by looking at it? One of them 0. 0 comma something or something comma 0. So if your coordinate has a 0 in it, then your theta is going to be one of those. If it doesn't have a 0, then you got to go through those formulas. That'll give you your theta. To get your r, use Pythagorean theorem. Okay. Any questions on that? Okay. So first, we're going to just practice taking a number that's not in trig form and writing it in trig form. And then after, I'm going to show you 2 out of the 4 things you can do faster in trig form. The 2 easy ones today. Okay, so write that in trig form. So keep in mind what you're looking for. This is the format that they want. Whether you do r first or theta first, it doesn't matter. They're totally separate. Let's do r. Somebody give me my equation that I would use. Just set it up for me to find r. Yep. Negative 2 squared plus 2 squared equals r squared. Now, he didn't have to worry about the quadrant it was in, because Pythagorean theorem, that part doesn't matter. Quadrant is going to matter for the angle. So we're going to get 4 plus 4, which is r, that's r squared. So when you simplify it as much as you can, what's r?
2 square root 2.
Yep. If they want a decimal, you could just type that in. Okay, so when we write our final answer, that is going to go there. Okay, next thing. We've got to find theta. Now, there's 2 formulas for theta, and the formula you use depends on what? Depends on the quadrant. If you want to graph it, you can. If you can visualize the quadrant in your head, that's fine too. What quadrant is negative 2 in? It's like right there. Left 2, up 2. What's the formula to find theta in quadrant 2? Yeah?
Theta equals pi or 180 plus the inverse tan pi over x.
Yeah, I was just going to do it in degrees. So 180 plus inverse tangent of y over x. Which number there is y?
2.
2. And which number is x? So I'm just going to plot that. So y divided by x in this case, it just comes out to negative 1. If you type in inverse tangent of negative 1, you will get negative 45. You just type it in, that's what the calculator will tell you. And what's 180 minus 45? 35. There's your angle. Now, it didn't happen here, but sometimes, like, if you might get a negative angle. Sometimes. What can you always add to a negative angle to make it positive? You can always add 360. Right? And that could happen if your answer was in quadrant 4. You wouldn't be adding the 180, so it wouldn't make this number positive. Okay? So like if the coordinate was 2, negative 2, you would have done the same thing we just did without the plus 180. You would have got an angle of negative 45, which is the same as 315. Okay, so sometimes they might ask you to add 360 to make a negative angle positive. They would not ask you to add 360 there. It's already positive. Okay, so now write your final answer. Just fill in those 3 spots. So, r cosine theta plus I sine theta. And do we do anything else with that? No, stop. Okay. I'll show you what not to do unless you're trying to check your answer. Take the cosine of 135 and distribute 2 times the square root of 2 times 2 square roots of 2. You got negative 2. Look what you started with. Negative 2. So if you distribute that out, you're going to get back what you started with. So you can check your answer if you want. Any question on that?
Could you do it with sine too?
Yep. If you took the sine of 135 and multiplied by 2 root 2, you would get 2. Yep. So it would be undoing what you just did. Okay. So, the trig form of a complex number basically gives you a very quick way to multiply and divide. I'm going to show you very quickly how we used to divide complex numbers by multiplying by the conjugate. Okay? I'm just going to go through it pretty much as fast as I can go through it while still trying to say stuff out loud. Okay? We did this back, I think, when we talked about quadratic equations. We did quadratic formula with imaginary answers. So it was way back in like chapter 2, or I think it was chapter 2. Okay. So you've got a complex number there, and if you wanted to divide it, this is how you'd have to do it. First, you'd have to remember, oh yeah, when you want to divide, you multiply by the conjugate. So that's not hard to write down. Conjugate is just you change the sign of the imaginary part. Now you have to distribute everything out. So in the top, you get 15 minus 3i. In the bottom, there's a trick because these are conjugates. You can FOIL it, but a lot of it's going to cancel. So you get 5 times 5, negative 5i plus 5i. That would cancel, so I don't need to worry about it. Positive I times negative I is negative I squared. But now I have to remember something else about I squared. That's equal to a certain number. Does anybody remember what I squared is?
-1.
It's negative 1. So now I have 15 minus 3i over 25 minus negative 1. So that's really 15 minus 3i over 26. But then you have to write 26 separate in each part. 26 and 26. And that's the old way to divide complex numbers that we did a long time ago. So it's not super hard, but there's a lot of little things. Conjugate, FOIL, change I squared to negative 1, combine like terms, separate it into 2 fractions. If we can write complex numbers in trig form, we don't have to do any of that. All that goes away, and you can pretty much just do the answer in your head. Okay. Where that, most people aren't going to be able to do in your head. And even if you could, then I could just make this one even worse. Now you have to FOIL in the top, and you have to FOIL in the bottom. So now it's even harder. Okay. So, suppose that you had 2 complex numbers. Okay? Each complex number has its own radius. Each complex number has its own angle. Just like our problem had 2 root 2 as a radius and 135 for the angle. Okay. If you want to multiply, we'll do multiply first, and then I'll show you divide. If you want to multiply those 2 numbers together, the old way is FOIL. FOIL everything out. The new way, it's going to be a lot easier. All you have to do in the new way is take the 2 radii, which are either given to you or you have to find, the way I just showed you with the Pythagorean Theorem. Take the 2 radii, multiply them together. Take the 2 angles and add them up. And that's it. So to multiply 2 complex numbers in trig form, you only have to do 2 things. Multiply the 2 numbers in front, and then add the 2 angles together. We're going to try 1 multiply, and we'll do probably 1 divide. Divide is very similar. The old way, I just showed you guys. Conjugate, all that stuff. What do you think, to do it the new way, what do you think you're going to do with your R1 and R2? You're going to divide them. And what do you think you're going to do with theta 1 and theta 2? You're going to subtract them. So now to divide two complex numbers, if they're in trig form, that's the whole key. Are they in trig form? If they're not in trig form, maybe this doesn't save you time then. Okay? If they are in trig form, it will. Take your two radii, divide them. Take your two angles, subtract them. It's important that R2 is not 0, because you can't divide by 0. So I would never give you one where it is 0. Any questions on that? Those are your 2 points. So let's take a look at one. I might fix the problem a little bit because I just saw it and I may want to change something. So this point, I'm going to do it in degrees. So I'm gonna fix these. So we did this one together. -2 plus 2i. The radius was 2 root 2. What was the angle?
135.
It's 135. 135. Now, this one I want to do in degrees as well. So I'm going to quickly find the angle of 3 plus 4i. Now, I didn't erase the radius, because if you do something in degrees or radians, does that affect how far it is out on the circle? No. The radius is just like using a ruler. It doesn't use degrees or radians. All right? What quadrant is 3 plus 4i in? 1. And what's your formula to find theta in quadrant 1? Inverse tan y over x. Now, unfortunately, a 3, 4, 5 right triangle has a nice hypotenuse. The angles are not nice. They're decimals. So, inverse tangent of 4/3. We're just going to call it 53.13. Okay. And now I want to take z1, z2, and multiply them together. Old way, I would be foiling 3 plus 4i and -2 plus 2i. Now we're going to do it the new way. Okay. When I do z1 times z2, what's going to be my new radius? What is it? 10 square roots of 2. Cosine. And what am I going to do with the angles that I have? Add them. 135 plus 53.13. Done. That's the whole problem. No I squareds to change the -1s. Nothing. That's all you got to do. 188.13. Cosine 188.13. Okay. Now let's divide them. Okay. What's my radius for z1? 5. And what's my radius for, I'm just doing it off to the side, for z2? 2 square roots of 2. Okay, so that's my new radius, but what do I have to do with that? So we're going to get 5 square roots of 2 over 4. When you multiply top and bottom by root 2, we get root 4 in the bottom. So that's going to be 2 times another 2. Because the square root of 2 times square root of 2 is 2. Okay, so that's my radius. And what do we do to get our angle? Subtract. So this is where I told you something could happen. It's going to be a negative angle, which by itself, that's not technically a problem. If they don't say negative angles are a bad thing, we can leave it as negative 81.87. So 7 plus I sine negative 81.87. That's fine. But if they wanted that angle as a positive, what would you have to do? Add 360. So take negative 81.87, add 360, and that is one way to make the angle positive. It's 278.13. Plus I sine 278.13. Now, there's one other way to make the angle positive. What did we say? And we talked about this when we did sum and difference. If you have a negative in front of an angle and you're taking the cosine of it, what can happen to that negative? It can just go away. The cosine of negative 81 versus the cosine of positive 81. You actually type 81. It's the same thing. When you have the negative and you're taking cosine, you can just get rid of it. Which I think is even easier than adding 360. So you could say 5 root 2 over 4 times cosine 81.87. Now, what about when you have a negative with sign? You can move the negative in front. You can't get rid of it. But what you can do is, like if you had sine of negative 15, that's the same as the negative sine of 15. You can move the negative in front. So this plus would become a minus. Sine 81.87. All three of these answers are correct. If the directions didn't say which one on a test, they're all fine.
Would there still be I?
Yes. Yeah, they all have to be cosine plus I sine. Notice in all three versions, the radius doesn't change at all. You're just playing with the angle to make it positive, doing it different ways. Okay. Any question on that one? All right, let's just convert. Let's just practice converting those to trig form, and then one of the homework questions will be having you multiply and divide them. Right, but let's do part of it now. All right, negative 2 plus 2i. Did we already do that one?
Yeah.
Yes, so that one's already done. So z1 is 2 root 2 cosine, I think it was 135. So I use that one just to save a little time. But now let's actually practice one we haven't done. Okay, z2. What quadrant is z2 in? Quadrant what?
Quadrant 4.
So positive, negative, right, down. So that would be quadrant 4. What's your formula to find theta in quadrant 4?
Inverse tangent y over.
Do you have to add 180? No. So inverse tan y over x. So what's y?
Negative 3 squared.
Negative 3 square root of 3. And x? 3. So really I could just do inverse tangent of negative square root of 3. Negative square root of 3. So that's an angle of negative 60. Which, let's just make it positive by adding 360. So what is that the same as? 300. So there's your angle. And what's the other thing I need? Radius. And how about Derek? What's my formula with the numbers filled in to get that?
3 squared plus 3 square root 3 squared.
Now, technically it's a negative, but it doesn't matter because when you square it, the negative goes away. Now, this 3 squared root of 3, it looks like it could be a pretty lousy number, but notice how nice the angle worked out. Maybe the radius will work out nice too. Or at least when you square this, it won't be that big. 3 squared is how much? 9. How about 3 square roots of 3 squared?
No, that's gonna be
That's
the
50 squared.
So it's going to be positive, but what is it? 27. Any question on how to get that? Okay, so we got positive 27. So what's R? 6. Very nice answer. So, what would be my answer to write Z2? Yep. Cosine 300 plus I sine 300. Okay, so now you have Z1 and Z2 in trig form. We can very easily add or subtract them. Either multiply the radii and add, or divide the radii and subtract the inverse. Okay, so any questions on what we did today? So like I said, I think it's a little bit harder than the law of sines and cosines, but this section's not too bad. Tomorrow's kind of like today. It's similar. It's less stuff because you already have all the background information about how to write something in trig form. So it's just 2 more things, powers and roots. All right, so that is the homework from tonight. And take example 6 and just do Z1 plus Z2. Right, so page 450, those questions, and then example 6, just Z1 plus Z2. You don't have to divide.
Is that the last one?
That's the last one we just did. And we already did half, well, more than half of it, really.